Neeraj Dhanwani. Okay, so he will speak on commutativity of periodic mapping classes. So yeah, I request Neeraj to start.
Yeah, are you able to hear me?
Yeah, we can hear now. Yeah.
Sure, thank you. So thanks for this wonderful conference. And when we can not do anything, then we can do a mathematics. That's like okay. So I'm before I go to the explain every word in the title, I am starting my talk with a little motivation. So what is the meaning of the commutativity of the periodic map, and why this problem is interesting? What I'm going to discuss, this is based on this paper, which is recently published in Geometry Educator with my supervisor. So consider this three diagrams. These all are the different embeddings of the genus 8 in the R3. So if you take this embeddings of genus 8 in R3 and you consider these as axes, which I denoted by the arrows, the x and y and x and z axes, then they all are the same kind. What the meaning of the same kind? I have that they all are going to be the fixed 2 points and the permute 4 genus in pair. So they all are the order 2 maps which going to fix exactly 2 points where they are intersecting with the surface. What about their composition? So what about when they will commute? So it's not difficult to see in this diagram that whenever two involutions in R3 make a 90-degree angle, then they will commute. But in the third diagram, they will not, even though they have a same kind what the previous diagrams have. So they also have a 2 6 point. So this motivates us to find a condition when two mapping classes have commutativity in between them. So before again to make precise to definitions, let's recall all the definitions what we have. Throughout this talk, SG will denote a closed surface orientable surface with genus G. Homeo plus SG is a collection of the orientation preserving homeomorphisms. Mapping class group is defined as the isotopic classes of the orientation preserving homeomorphism. Because here I'm not talking about the boundary and punches, so I'm not bothered about that definition, but this definition is defined for that too. For me, everything is very good. Then this is a very basic theorem in our direction is Nielsen-Kirchhoff theorem, which says about something about the finite order mapping classes. So Nielsen claimed in 1940s that if you take any finite subgroup of mapping class group, then there always exists a hyperbolic matrix such that under that matrix can be realized as a group of the isometries, which technically in the easy sum says for every finite order mapping class you can associate a finite order homeomorphism. So the benefit of that is because this is an isometric group, you can talk about the quotients. You can talk about the properly discontinuous action of that. Before going to properly discontinuous action on the surfaces, we define some properly discontinuous actions on the known thing, PSL2R. So consider a discrete subgroup of PSL2R, which is a PSL2R is an isometric isometric group of the upper half plane. So if you have a compact quotient, then it have this form. Whatever the form is written here, the group have to be this form. And when this I'm talking about a quotient, compact quotient, that means this gamma is acting on somewhere, and this is acting on this natural choice of the upper half plane. So because I am dealing with the PSL2R and everything, so I will restrict myself for genus greater than 2. Even when you are genus less than 2, this commutativity problem is pretty much easy because the groups is very well known. For the sphere, the mapping class group is trivial, and for torus, the mapping class group is SL2Z, in which we already know there is no commutativity and something like this group is well known. So This problem is much more makes sense when you are talking about a genus greater than 2. So go ahead. This theorem is very classically known in the group actions, that a finite group act on the surface if and only if it satisfies such a sequence, exact sequence, where this phi is a, we say, is surface kernel, and this gamma is a friction group, which we generally know as a orbifold. So orbifold is a topological meaning to this group, which is given by the Thurston. This theorem is make more precise by the Harvey for the cyclic groups. What he proved, that this homeomorphism friction group on the finite groups H is surface kernel. That means it's a surjective, and the kernel is pi1 of Sg for some g, if and only if it preserves the order of the finite order element. That is, there is some elements which have the finite order and some have infinite order. So on the finite order elements, this map is injective. That is, if zeta 1 have order ni, then phi of zeta 1 is also have order ni. So now for the group, it's important to understand only this phi. So when the group is cyclic, you put H is cyclic. This map is technically can be achieved where the zeta i's are going, because this group is cyclic, is generated by one element. So every element can be written as a power. So you can write zeta I to be some power of the generator. So power is always you can write as a n over ni over n, where n is the order of Zn and ni is you are taking the order of this thing, and some multiple of the Ci. So you can map to your zeta 1 to ni over n times Ci, and that is a precisely order ni word. So you get this type of tuple. So this n is tells what is a group, order of the group. G0 tells what is a quotient orbifold. R is something which I am going to be explained. Ci, ni is that numbers. So this tuple is going to correspond this map whenever you have a Zn in the right hand side. But what about the converse? If I give you this tuple, can you always build up such a map? Yes, if this tuple is going to satisfy this five conditions. The last condition is a Riemann-Hurwitz condition, which is just a generalization of the Euler characteristics in the case of the orbifold. If you remove this part, if you remove all the cone points, then this is a precisely a Euler characteristic for n order cover, n sheeted cover. The condition 4 is about the generator condition. The map is onto. Then 3 condition is about the finite order preserved, and this is about to satisfy this long relation, that the product of all the commutator with the product of all the finite order elements is 1. So all the images is also 1. That's this condition. So technically, this tuple is going to be correspond with the one, this surface kernel map. And this is shown that this data set, now this I call this a data set, is one-to-one correspondence with the conjugacy classes of the finite order elements in the mapping class group. So now to give the conjugacy class of the finite order element in the mapping class group, I will always deal with this data sets, which are the easy to handle in the combinatorics. So now we have talked about some algebraic aspects, some going to be some topological aspects. So okay, so before that there is some notation. Let F be a mapping class, then its conjugacy class I am going to denote by DF, which is a data set of F. I will denote OH is a quotient orbifold by the group H. Whenever H is a finite group, even you can denote it for the infinite group. For me, always a finite group. So it's a quotient of Sg quotient by H. H is a finite subgroup of mapping class group. And by Nielsen-Kirchhoff theorem, I can correspond to the homeomorphism and the isometry. Okay. So now is some properties of the commutative map. What is the property they have? So first property they have, if they commute, they are going to be induce some action on the surface. and they satisfied such a property that induced action is also have to be order n if they are not power of each other. By this, what we have, that is some necessary condition, and that necessary condition we want to make the two sufficient also. So we put some conditions on the induced map, and we call these tuple to be the essential pair. If you can find a map on the homeomorphism on quiescent surface such that it induced a map on the orbifold which satisfied the induced map property, which we have shown before, that it have to be respect something. The same with the G bar, G tilde also. So for the F, when you first quotient with the F, G have to be induced that map. If you quotient by the G, F have to induce that map. And they also together have to give the same orbifold when you're going to be final quotient. This property we go to call is the essential pair, and we define what the meaning of the weakly commutativity. The weakly commutativity is means when they commute in the conjugacy class. What that means is, if you take a two element, you say they are weakly commute if in the conjugacy class of X you can find a one element, and in the conjugacy class of Y you can find a one element such that they commute. With these two definitions, we have our main theorem. Our main theorem says you take F and G in the mapping class group, they will weakly commute if and only if they will form a weakly abelian pair. So what is the meaning of the weakly abelian pair? The weakly abelian pair is nothing, is just an essential pair with one more technical condition, and that's a little bit technical. But even most of the cases, that's not going to play a role. Even I will show in the one example of the involutions, there is no such a role. But that's a technical for the most of the examples which I'm going to I will not cover in this talk. Okay, so before go to the some more visualizations, first some applications of this theorem, some easy applications. Primitivity of the mapping classes, finite order mapping classes. So what the meaning of the primitivity is, if you are talking in any group, you can talk about the some h such that h to the power n satisfied the G. So this h we call the root of G, and the root degree of the root is n when this satisfied this condition. So for the finite group, it's always there is a thing, but for infinite group, maybe such a thing is not possible. For example, if you take Z, then 1 is only have -1. Oh, yeah, -1 with a multiplication. Such a thing is always. So if you take a G is a non-trivial, have no non-trivial roots, then it is said to be primitive. What the meaning of non-trivial roots? When you can write G as a h to the power n, but their order is precisely the same. Like in Z3, 2 and 1, both can be written as the power of each other in Z3, but they are the same order. So I will call the trivial roots. I only discuss the non-trivial roots, and if they have no non-trivial roots, we call it primitive. So again in Z3, 1 and 2, both are the primitive. So in Z4, all the generators are the primitive, and that's a meaning of the taking a Zn star. So in the mapping class group, we have shown that what are the we have given the condition to be the primitivity, which is kind of same to our main theorem, but much more easy sense, because in this condition you are dealing with the same f and f to the power something. So if you have order f is 6, then you are dealing with the f square and f cube, which are the same map. But the corollaries are the very interesting and easy to explain, that if you have a mapping class which is a free action means it don't fix any point on the surface. So this is we called as a regular map, regular cover. So if you take the orbit of the f of any point, it have a same cardinality, which is the order of the f. Then this have a non-trivial root only if the quotient orbifold is not spherical and the root only can be degree 2, and that is only if G minus 1 is not divisible by the 2. The second application is about the free actions. So again, when you have a free action, you can talk about the commutativity. but that commutativity is fine, but what you can achieve by that more, the achievement is more is this: when you have a free action and commutativity, suppose your F is free, then you have a G which commute with the F. So G induce a map on F, quotient of the F, which is again a compact surface. So what is the reverse? What is the reverse means? What is the liftability problem? So if you have a surface below, when can you find a lift such that the lift will commute or the lift exists? So we are giving this problem answer is there. So F is the mapping class of the finite order such that orbifold is not spherical. Then you can always find a lift of F in this finite sheeted cover. This liftability, I think, is well known in algebraic topology problem. Again, one more example is commuting involutions. Here the things are easy because involutions means order 2 map. And the problem I am putting like this: if you take a 2 involutions, when you are going to be commute, and if they commute, what about how many different ways? So these are the two problems are there. So our corollary of the main theorem is this: if you have these two involutions, one is this and other is this is saying just a permutation of the genus with this many fixed points and so on. Then they will commute if they satisfy this property. And this corollary is the proof of this corollary not only says they will commute, but also says how many times, how many types of different client for group they can make. So this is a calculation when the K3 is this, and for our example, these are the three possibilities, and I'm showing the pictures of that, how you can visualize them. So these are the three visualizations of the client for group. So our paper is going to be not only talk about the when they commute, is also give the hint that what is the visualization of that commutativity diagram. I think I am on time.
Okay, thank you, Neeraj.